Okay, this is the second half of the first problem. We didn't really do anything last time except talk about it. And I did forget to talk about one thing, and that thing is, in problems like this, I didn't really specify how wide the output needs to be, and typically you want to keep it as small as possible to do the job. Okay, so for this problem we're adding 32 8-bit values, so essentially that the width needs to support 32 times 8, which is, I have no idea what that is, but as far as we're concerned, we can do this in binary. So 32 equals 2 to the 5th. Essentially what I'm going to do is 2 to the 5th times 2 to the 8th. 2 to the 8th, essentially the biggest an 8-bit value can be, which is 256. It's actually 255, but this is close enough, equals 2 to the 13th. So what we're interested in there is that value of 13. Okay, so that 13 is going to be enough bits, 13 bits, to hold 32 times 8. Once again, I did it in binary so I didn't have to do the math on this thing. Okay. So here we are ready to go in this problem, and we talked about the parts it needed before, and it certainly needs a RAM, so we'll toss that in there. This is 32 by 8. We need a counter because we agreed that the counter's output is we're going to use that to drive the address of the RAM. So we'll put that in there. We agreed it was going to be a 5-bit counter. This is the address input. We don't need to write anything in this problem, so we'll take that a write enable, tie it to 0. It is a clocked input, clock circuit, so we did a clock there. Counter's clocked also. There's the clock signal. I'm not going to fill that in. Typically I don't put clocks in there because it messes everything up. And so what else do we need in here? This is going to be an up counter. So, and it's always counting up, so I'm going to go ahead and put an up in there and tie it to a 1. This is my way of indicating 1. So it's always counting up, except of course when I clear it. So this is going to be a counter that has a clear input as well. So I'm going to be able to set this counter back at 0. So the other part of this problem is going to have an accumulator, and the accumulator is going to be a ripple carry adder and yet another register on this thing. And we agreed the output of this thing is 13 bits. I'll just call it result for lack of a better word on this thing. Okay, so this is a standard accumulator setup here on this thing, and what it's going to be doing is adding 2 values, which is, I should have fixed that up. Should have fixed that a little bit better. Okay, so what I'm going to do here is append 5 bits, 5 zeros. Okay, so I'm putting 5 zeros on this to convert it from an 8-bit value to a 13-bit value. Essentially this is 0 extension, add 5 bits to the end of it. So what I'm trying to do here is add up 2 13-bit values, which is essentially A and B here. So this adder is adding these 2 values. The output is going to be 13 bits, and essentially this is what I'm going to be loading into this register at the back end. So this is a register. It's also a clock circuit, so I'll put a clock in there. It's a synchronous circuit. And the other thing I need to do here is I need to control when the circuit's loading. And so I'm going to put a load signal on it, known to be a load control. I'll put a load there also. And lastly, I think I need to be able to clear that register because this is accumulator. I'm adding up values. Certainly I'm going to start that accumulation at 0. So I need to be able to start the register at 0, which is a good place to start any count. Okay, and I think that's all I need on this thing. I do need a state machine, so I'm going to put that state machine in here, FSM. And typically the way I do this is collect these signals, and essentially the left side of the inputs to the state machine are going to be status signals, and what I have here is one is the go, which I forgot to put in the problem. That's going to start the problem off, and I just remembered I need another status signal, and essentially this is going to be ripple carry out. The ripple carry out is going to tell me when this counter hits its terminal value, which is 11111. Okay, so I hope you use ripple carry outs in your class. We used them extensively in my class. It's a very handy signal. So once again, that's going to tell me when to do something different in the circuit. So this RCO here is a status. It's a status signal, and it's going to go into the state machine. State machine is also clocked. I forgot to put the clock in the bottom in this thing. And then what else do I need in this thing? So I have two control signals. I've got this up is a control signal. I don't need to worry about it. I do need to worry about that up signal, so I'm going to have to fix that. Let's go ahead and erase that. No big deal. Sorry about that. Whatever, I make mistakes all the time, and then I go back and fix them. So I've got a couple different control signals now. One is up, one is clear, one is load. And I think I'm ready. I think I'm done with the circuit part of this. What I need is a state machine to control this thing. So what I'm going to be doing in this thing is to essentially, I'm going to try to break it down to what am I doing. I'm doing two things. One, I'm waiting for someone to press a go button or a go signal, and then when they press that, I'm going to start doing a bunch of additions. Now the issue is that's all I'm doing. I'm doing two different things here. Essentially, I'm going to be able to represent that in two different states because, essentially that's all I'm doing, but also I'm going to use a Mealy type machine in this. Okay, so here I go. The two states are essentially going to be some type of wait state and some type of count state. Okay, so these are state machine. State transitions happen on the clock edges, and so I don't need to put a clock in this thing. And so let's see. What the question is, what keeps me in this state? What keeps me in this state is the fact that I don't get a go signal. Okay, but I do get a go signal, I go to some other state. Now I'm going to put an overbar over that, indicating the go is not asserted. I do get a go signal, I go to the count state. So for each one of these states, I need to account for every single one of those outputs. So what I'm going to do here is for this counter here, I'm going to look at it and say up. What is up doing in this state? Up, I'm just going to turn it off. Okay, so what is load doing? Certainly in the wait state, the load is turned off. And in the clear is an important signal. I could make this into a Moore machine and put this inside the state, but I'm not going to. I'm actually going to make it, make it into a Mealy machine and put this clear output on the outside. So essentially the clear signal is now a function of both the state and the input, and the input it's associated with is the go signal. So if I don't get a go signal, I'm not going to clear this thing. If I do get a go signal, I'm going to clear this counter. Okay, and once again I've accounted for all three signals in the state, three output signals, these three outputs of the state machine, which are control signals. There they are. I'm done with the state. So in this state, I'm going to be doing the counting, and so once again, I'm going to have to handle all these three signals again. So let's do it. So up, in this state, I'm going to be counting up in that counter. So I want to increment by 1 every time it gets a clock signal. Essentially, I'm also going to be loading the accumulator here. I want it loading in every single clock signal. That's 2 of the signals, and the clear. And in this state, certainly I don't want to be clearing anything. I can actually treat this as a more input in this state. It works fine. So what keeps me in this state is the fact that RCO is turned off. Okay, so once I get an RCO, I am going to say I am done, and then I'm going to transition back to the wait state. And at that point, I'm going to check this thing out here. I've got 1, 2, 3 signals. I've accounted for all 3 control signals in the wait state. I've accounted for all 3 control signals in the count state, and then I'm done. So this is going to be a real summary here. Some go button's going to turn on. It's going to clear the counter, cause it to transition to the count state. Inside the count state, every clock signal, I'm going to be incrementing the counter, which is going to be the output of the counter. It's going to be used as an address into the RAM. It's going to output a new value every single time. And every clock edge, because I have an accumulator here, is going to accumulate the current value of that register, which is the A input, to the current output of the RAM. Okay, so that's the way I'm going to add these things up. I'm going to do that 32 times, and once that happens, the RCO is going to turn on, which is going to cause me to transition back to the wait state, and I'm going to call this done. Yes, and I did rush this because I wanted to be able to fit onto YouTube, so I apologize.